Alright, so having finished with exponential functions, we're going to move on and we are going to look at logarithmic functions. So logarithms are defined by their inverse relationship with the exponential functions. We'll talk about inverse functions in general in another video, and we'll talk about it in class as well once we get to derivatives of inverse functions. Um, but let's remind you how this goes. So how do we define a log function? So logs have a base just as exponents have a base, and that base has to be some positive real number. Okay, and we define the logarithm in terms of its relationship with the exponential function. Okay, so if I plug a number x into the log function, what should the output y be? Well, y is whatever number, oops, this should be an a. Y is whatever number I need, whatever exponent I need, so that a to the power of y equals x, right? So it's kind of, it's reverse engineering the exponential function, right? I want my exponential function to give me a particular y value, and I'm trying to figure out what x value I need to obtain that y value. So that's what the logarithm is doing for me. Another way of thinking about it is that the logarithm and the exponential function, they cancel each other out, right? So if I take some number x, I raise it to, I exponentiate it, so I take a to the power of x, and then I take the log, I get back to where I started. And similarly, if I take the log of that number and then I take a to that log, I get back to where I started. So we get this inverse relationship. The natural log has its own notation, this ln. This is used when you're dealing with base e, so the inverse of the natural exponential function is called the natural log. Some people like to pronounce this as ln. I don't know, somehow that hurts my ears, so I will usually just say natural log or maybe ln. You won't catch me saying ln except for just now. If you really like saying that, feel free. I think it sounds weird. Anyway, continuing on. The logarithm functions have their own properties, and these properties are all inherited from corresponding properties of exponential functions, right? So the fact that when you multiply powers, you add the exponents, right? The logs, the log function is giving you the exponents, and so what this means in terms of the logarithms is that if you take the log of a product, that should be the same thing as the sum of the logs, right? And similarly, the log of a quotient should be the difference of those logs, and the log, if you have a log of a power, you can bring that power out front, right? So you can work these out. I'm not going to do it here, but you can, using the definition of the logarithm from the previous page and the laws of exponents, you can derive all of these properties by playing around with the definition and the laws of exponents. A few other things to note. Well, since we have this inverse relationship, and since the exponential function, exponential function is never going to return a negative number. It only returns positive numbers. You can plug any number you want in, but you only get a positive number out. Since the job of the log function is to kind of tell us what the outputs were from the exponential function, well, if the exponential function has only positive outputs, that means the log function can only accept positive inputs, right? So the domain of the log function is positive numbers. But any number can come out in the range, right? So the range is everything. Just to kind of illustrate the relationship here, let's jump back over to GeoGebra and we can see the relationship. So our exponential function is there in blue, and now we've also plotted the corresponding log function in red, and you can see this inverse relationship. You might have one of the things that you might have been told at some point, right, is that one of the ways you get the graph of an inverse is you reflect. You reflect across the line y equals x. And you can kind of see that here, right? There's the line y equals x. The graph of the log is the mirror image across that line of the graph of the corresponding exponential function. And again, you can play around with the value here, and you can see how those change as you move through different values. Okay. And you can see this inverse relationship between the two. Okay, all right. There we go. Okay, we'll stop playing with that. Notice that the graph you can see the graph looking, at least for numbers, values of a bigger than 1. You see the graph passing through the point 1, 0. When x equals 1, y is going to be equal to 0. It heads off down towards minus infinity as you get closer and closer to 0. And it very slowly climbs up. As x goes off to infinity, the y values will also go to infinity, but very, very slowly. Okay. So one of the things that will be useful for you in this course is being comfortable working with these properties of logarithms. We're going to see that there are certain, derivatives and integration problems where you can simplify them quite a bit by playing around with logarithms. One other property that does come up, and for the most part we won't need this because we're going to be working almost exclusively with the natural log, but there's this change of base formula that allows you, if you're given a log function in some sort of unusual base, like you're doing base 2, base 3 or something, and you want to convert to the natural log, this change of base formula will let you do it. One of the reasons why you might need to do this, there's no real compelling reason to do it when you're working on paper, but if you actually need to compute things and you're using your scientific calculator, chances are your scientific calculator has buttons for the natural log and for the base 10 log. It's not going to tell you how to do a base 2 log on the calculator unless you've got a particularly expensive one. So the change of base formula allows you to move between different logarithms if you have to do it. So that's something to keep in mind. Now, as for working with the other properties, here's an example. I'm given the value, I've got 3 numbers, a, b, and c. I know what their log values are. I know what their natural log values are, okay? Log of a is 2, the natural log of b is minus 3, the natural log of c is minus 1. I want to know the value of this scary looking thing here. So how do we work this out? Well, we're going to work it out using the properties of the logarithms. And one of the things that I want to kind of be careful about here, point out, notice that these log properties, you always have the log on the outside, and it's telling you how to deal with certain types of inputs. If your input is a product, a quotient, or a power, these log properties tell you what to do. If there's something going on with the logs, like if the logs are being multiplied together, raised to a power, if you see more than one log function in there, there's actually nothing you can do to simplify. Okay, so the fact that I have this log multiplied by this other log, there's no rule that lets me simplify that. The fact that this log is raised to a power, I've got no rule that lets me simplify that. But what I can do is I can simplify this term and I can simplify that term. So let me do the first one. So the natural log of a cubed b squared over c to the 5th is, so let's use the quotient rule first. I can write that as now a cubed b squared minus the natural log of c to the 5th. I'm going to include all the steps, by the way. Once you get comfortable with this, you will probably skip some of these steps. Now I use the product rule for this guy. That's supposed to be a 2. B squared c to the 5th. Now I can bring my powers down in front using that third property. 3 log a plus 2 log b minus 5 log c. Oops. C. Now I can plug my numbers in. 3 times 2, 2 times minus 3, minus 5 times minus 1. So that comes out to give me 5. Similarly, I can do log of ab cubed, and let me do this one quickly. That's going to be log a plus 3 log b. So that's going to be 2 plus 3 times minus 3, which is minus 7. And so what is this quantity that I want to calculate? Well, it's going to be, the first thing was 5 times minus 7 and then squared, right? So minus 7 squared is 49, so that's 5 times 49. Work that out if we really wanted to. 245. the final number isn't all that important. The main thing is being able to work with these log properties. Okay, that's it for logarithms. We're about ready to start talking trig, and that should be the last thing we need to do for these review videos.